So before we move into using the critical points in order to find the local and absolute extrema, I want to first talk about the relationship of the first derivative with the shape of a function. And this is something that I've kind of mentioned in passing already, and you might have already caught on to just doing some problems. But I just kind of want to formalize this idea, and we actually looked at this explicitly in the mean value theorem video when we showed that the mean value theorem tells us that a function where the first derivative is positive is always increasing. Okay, so we can extend that past the entire function needing to have a positive first derivative. Just in general, we can say let f be a function. Let f be a function. Then when f prime of x is greater than 0, f is increasing. Okay. So in other words, if there's some interval a to b where f prime of x is greater than 0 on that entire interval, then f is increasing on that interval. Okay. On the flip side, when f prime of x is less than 0, f is decreasing. Okay. And if you don't remember the definitions of increasing or decreasing, it's just what you would expect, right? That the graph is the f of x values are going up, so the graph is going up, right? The function's going up on the graph. Formal idea would be for increasing, okay, that a is less than b implies that f of a is less than f of b, right? That would be the idea of increasing. And decreasing, a is less than b would imply that f of a is greater than f of b. So these are the two situations we can have with the first derivative, and of course if the first derivative is equal to 0, then f is constant. Okay. So we've kind of already seen this idea when we've talked about the derivative of a constant function is 0, right? That's the only time we've seen the derivative be 0. And it is the only time where we would see the derivative be 0 everywhere is if we had a part of the function which is constant, meaning it's neither increasing nor decreasing. It would just be a horizontal line on the graph. So this can help us get a much clearer picture of the behavior of a graph of a function. And we'll be able to get even a clearer picture once we start talking about how the second derivative affects the shape of the graph. But first I want to just go over this part, and then we can move into the critical points and the local extrema with this. But let's just do some examples where we can try to get a clearer picture of how the graph behaves, using this. So let's use our trusty x squared example. The derivative of x squared is, of course, 2x, which we've seen plenty at this point. So if we just look at how the graph of 2x behaves, and I'll put this on Desmos too, so we can get just a better picture of it. It doesn't really matter what the values are. If we're just looking at increasing and decreasing, it really just matters whether the derivative is positive or not. So if I kind of overlay these, so I'll just go ahead and overlay them here. So it roughly would look like this. Not drawn very well as usual, but we're just looking at if it's increasing or decreasing. So of course the blue line here is f prime, the red line is f. So we can see that when the derivative of f prime is positive, the function is clearly increasing, right? It's going upwards. And when the derivative of f prime is negative, the function is clearly decreasing, right? It's going downwards. So this again just connects back to the fact that the derivative tells us the slope of the tangent line to the function at that point. If the slope of the tangent line is negative, then the function would be decreasing, right? If I just like draw a tangent line here, right? In order for, basically when this line is decreasing, the function's also decreasing. And if this line was increasing, the function would also be increasing. So just to get a little bit of a better picture here, where it's better overlaid. So again, we can see that as the derivative is negative, the blue line here, the function is decreasing. As the derivative is positive, the function is increasing. And as we've seen, you can actually just, Desmos does have that tool where you can just graph the derivative of the function next to the function. If you just call it f, then you can just write f prime of x and it'll just graph the derivative automatically. And there's a example problem of it here in their list of examples. So this one, it uses ax cubed plus cx, and it has a little slider for you to just adjust the values of a and c, which is pretty neat. So if you just think about what the derivative of ax cubed plus cx would be, it would be 3ax squared plus c. Okay, so this part right here, what they're calling g of x, would be 3ax squared plus c. So a quadratic. So the purple line is a quadratic. And then the red line is the function, of course. So you can see this idea in action again. So just looking at the red line, we see that the function is increasing until about right here, what we would call the local maximum, right? And that corresponds to the derivative being positive until that exact same point where it hits 0, right? The derivative is 0 at that point, which means that we have a local maximum at that point. That doesn't mean by itself that we have a local maximum, but that's one of the conditions, right? And then the derivative is negative until this 1.65 point. So the function is decreasing until that same point, and then again you get a local extremum, a local minimum in this case because the derivative is 0, and then the derivative is positive, so the function is increasing from that point on. Okay. And then you can adjust the slider as you like. So an extreme case here, if we put a to 0, then that means we're just looking at the line cx. We can flip that around to make it a little nicer, right? So this is now the line y equals x, which has slope 1, right? So the derivative is constant, right? It's just, the derivative is just 1 in this case. 1 is a positive number, so the derivative is always positive. So this function is always increasing, okay? So yeah, I think that's, just trying to see if I can really make any more interesting shapes here. I think that's pretty much it for this polynomial. So let's look at some other examples now. So if we maybe look at some more special functions, e to the x, for example. E to the x is, of course, always increasing. If you look at the graph, right, it looks just something like this. I won't draw the whole thing, but it just looks like this. It's always increasing, going from left to right, which should be no surprise because f prime of x is equal to e to the x, which is always greater than 0, right? So it's always going to be positive. Maybe just to look at a trig example, tangent is a good one, right? F of x equals tangent of x. If you've seen this graph, either just in Math Tools 1 or on your own, again, I won't draw the whole thing, but it basically looks like this with like a series of identical functions that just keep looking like this, right, as they go. So, but the idea, of course, it's badly drawn because these can't be on top of each other, but the idea is that they are always increasing, right? There are those spots where they're not going to be differentiable at the asymptotes, but in general, these are always where they're defined. Everywhere in the domain of tangent of x, it is increasing, and that's supported by the fact that the derivative, as we found before, was secant squared of x. Right? We don't even really need to know anything about secant. Just the fact that it's squared is going to guarantee that it's always positive. Or 0. So this is greater than or equal to 0. So, and this really can't be 0 because if you remember, secant is 1 over cosine. So 1 over cosine, it can't be 0. So this is really strictly greater than 0. So that, again, tells us why that this function is always increasing. Okay. Another function that's always increasing that's common would be your natural log function. So this one might be, again, the graph of this one looks roughly like this, where it kind of flattens out, but it is always going upwards. So this one, the derivative itself is not always increasing in general, but if we consider only the domain of the natural log function, and specifically its derivative function is only defined when x is between 0 to infinity. So on that interval, this function is always positive, right? So because of that, the natural log function is indeed always positive. All right, what about a function that's always decreasing? Okay, what about, for example, take that derivative, 1 over x. What if we look at 1 over x? Okay, this function is always decreasing, right? If we look at the graph of this, it looks like this, where it's flat and then it goes down towards infinity. And then on the other side of 0, it's also going downwards. So it's always decreasing. Again, informed by the derivative, where this is negative 1 over x squared. Okay, x squared is always positive. So this is always going to be a negative number divided by a positive number. So this is always going to be negative, right? So that's why this function is always decreasing. Okay, so we've really only looked at functions which are strictly increasing or strictly decreasing. Only this one was really actually changing signs. So why don't we go ahead and look at one where there's possibly a lot of different increasing and decreasing intervals. Okay, so let's look at f of x equals x cubed minus 4x squared plus x minus 4. Okay, and this one, I think it's going to be a little bit messy when we actually go to look for all the places where the sign flips and stuff, but that's okay. We'll look at how to deal with that. So if we want to know where this function is increasing or decreasing, we need to know what the derivative is. Okay. So f prime of x equals 3x squared minus 8x plus 1. Okay. And this is not a super easy function to work with, but it's not too bad, right? It's a quadratic. It's just not going to be like easily factorable or anything, but that's okay. So if we look at, we want to look at where is this function positive and where is it negative. So whenever we want to look at where something is positive or negative, we can break out what's called a sign chart, which will let us easily keep track of this. Okay, so if you remember the sign chart from Math Tools 1, it's the same idea. If not, then the idea is that a function can only turn from negative to positive. In this case, f prime is the function we're looking at, not f. It can only turn from negative to positive when you go through the x-axis, meaning that the function is 0, or at a place where the function is undefined. So you want to put your zeros and your undefined numbers on the sign chart. So we could call them zeros or bad numbers. In this case, there's no place where the derivative is undefined because the derivative is a polynomial, right? So it's going to be a continuous function. But if you just, if you did have, like if you were doing one for the last one where we looked at 1 over x and the derivative was negative 1 over x squared, here the function is undefined at 0. So that would go on your sign chart because that's a place where it could change signs. In that case, it didn't, but it could, right? So on this one, we need our zeros. So that's why this one can be a little bit tricky. It's probably going to be a little bit ugly because I don't think that we can really factor this, right? So we want to take this and we want to set it equal to 0 to find the zeros. And unless I'm not seeing an easy one here, it doesn't look like it's factorable. So we would go for the quadratic formula in this case. So it's x equals the opposite of this one, 8, plus or minus the square root of 8 squared minus 4 times 3 times 1, okay, all over 2 times 3. So we would get 8 plus or minus 64 minus 12, so 48. Wait, that's not right. 64 minus 12 is 52, rather. Right, yeah. And then divided by 6. 52, I'm trying to think if you can make that simpler. That's 26 times 2, right? And 20, so it is divisible by 4. Specifically, it's 13 times 4, right? So you can pull a 2 out of this if you want. It doesn't really matter too much. You're going to want some kind of decimal approximation probably to see exactly where this lands anyway. But you could write this as 4 times 13. So this is 2 root 13 over 6. And then you could cancel a 2 out of everything. If you want to make it a little simpler, right? It doesn't really make it all that much simpler. But these are our zeros, right? So 1 0 is 4 plus root 13 over 3. And then the other one is 4 minus root 13 over 3. Okay. So you could like try to approximate these because you don't really need to know exactly what these numbers are. You just need to know the numbers around them, like where the intervals are cut off. But you could just plug one of these into a calculator real quick just to get an approximation. So I'll go ahead and do that. So this one is about 0.13. And this one is about 2.5. So the idea with the sign chart, though, is that we just want to test numbers around these to see if the function is positive or negative, right? And if you don't have any what we call multiplicities, meaning zeros that are repeated, like they come from like a squared term or something like that, then these will alternate. So you really only need to find one of these, and then that'll let you fill in the sign chart more quickly. So, that's more of a Math Tools 1 topic. I don't even think we actually explicitly looked at it in Math Tools 1 because it's really just a shortcut But if you want to look into that, it's called a multiplicity. So anyway, the idea here then would be that we only need to test one number, so we could plug in 0 into the derivative and see what the sign is. So if we plug 0 into this, we get 1. So here it's positive, and then it's going to alternate. So it'll be negative and then positive. Okay. So that tells us that this function here is increasing. So maybe we'd write increasing from negative infinity to 4 minus root 13 over 3. And then from 4 plus root 13 over 3 to infinity. And it's decreasing from 4 minus root 13 over 3 to 4 plus root 13 over 3. Okay. So a lot of times when you're working with these, of course, the numbers are a lot nicer than this. I just wanted to use an ugly one as an example, just to kind of show how to work through it here. The quadratic formula also, if you ever need this, just as a reminder of what that is, it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, where you have a quadratic ax squared plus bx plus c equaling 0. This tells you what x equals. So this is mostly used when you can't factor the quadratic. So now we kind of want to investigate, okay, notice that these are, these increasing and decreasing, they're not including the endpoints here. So what exactly is happening at those in between points? Like what's happening at 4 minus root 13 over 3 and 4 plus root 13 over 3. And if you look at the graph, you'll see that's where we're going to have the local max and the local mins. And if they're increased, depending on where it's going from increasing and decreasing or vice versa, will tell us exactly which one it is without having to look at the graph.